So, back in 1.1, we were given this task where we had to make a pretty simple sort of abstract version of what we later ended up doing in the unit. And Max gave us a challenge of trying to do it in the least number of lines of code as possible. And I ended up with one of the more esoteric solutions in order to minimize the amount of lines of code I used. So with Max's blessing, I'm going to walk through that. And then because there's something wrong with me, I spent several more days, a couple weeks ago at this point, optimizing my original solution to make it take even less lines of code. But before we get into that, let's start off with understanding some things about the problem. And then we'll dive into the code, and I'll sort of switch back and forth between code and, I guess you could call it theory, just depending on what we need. So one of the first things that you need to think about if you're minimizing the amount of code lines that you want to use is that there are several things you need to do in the code, and then there's several things which you might want to do in the code, but which you don't actually need to do to follow the specification. For example, the code does not specify that we need a map object. So during the rest of the unit, we've obviously been using map objects, and we've had command objects as well. And at the end, we added user objects. But for this, we don't actually need a map object. We can find other ways to represent a map. We don't need an output. That's one way to save a little bit of code, is as long as we follow all of the constraints, all the requirements that are specified in this document, we do not need to have like a console output telling us the current status of the robot. And if we need to find that out, we can use the built-in debugger, or we can just sort of temporarily add some console outputs. So something to keep in mind is that we have a very limited number of possible inputs. Our program is essentially, at its very simplistic core, is a function that takes these inputs, and excuse my mouse writing, function that takes these inputs and provides some kind of output. In English language, we have these commands, and we need to turn those into coordinates. We need to turn that into directionality facing. But we don't have an unlimited number of things which we have to handle. There's only 4 commands: place, left, right, and move. And even within that, place has these parameters, but left is its own command with no parameters, right is its own command with no parameters, move is its own command with no parameters. These ones sort of have implicit parameters of the current state of the robot, because when we first start using the robot, we have to place it. Until we place it, it's not supposed to be able to do anything as the first constraint. It must ignore all commands until it's placed on the map. So implicitly, we sort of have the current state of the robot as parameters here. So we implicitly have X, Y, and we'll call direction D for each of these 3 commands. And that's important to remember. For example, if we're trying to move and we're at the left edge of the map, which could be represented if we have a map here, and we'll make it really simple. We'll make it a 2x2. So we have, this is 0, 0 for X and Y. That's 0, 0, we have 0 and 1, 1 and 1, and 1 and 0. So this x here is this x here, which is also these 4 numbers here. So if the robot is at 0, 0, and it's given a move command, we have to know what the current position of the robot is so that we don't let it go off the map on the west or off the map at the south. But it's okay if it moves north, and it's okay if it moves east. Same thing with if we're in 1, 1, we can't let it move north, we can't let it move east, but we can let it move west, that's fine. It's also fine to move south. So, I don't know what to describe next. There's a lot to cover, especially once we get into the more complicated stuff. So how do we represent the current state of the robot? Well, I've sort of answered that already. We'll represent it with an x coordinate, a y coordinate, and a d coordinate, which is just direction. How do we represent the state of the map if we're not using a map object? One way to do that is that every time we try to move, we check whether we would be going off of the map. That lets us compress things down a little bit. We don't need a map that way. It'll be messy code and code that's more difficult to read, but if we're optimizing for number of lines of code, that's one way to do it. Because these 3 commands all sort of have the same structure of command and then implicitly they use the current state of the robot, we can sort of categorize them together in terms of how we need to process them. And place, we need to process, well, we don't strictly need to, but we can process it separately to make our lives easier, and we can process these in a different way. So let's start off by figuring out how we want to process place. So we have specific syntax here. So let's remember, we have the expected command will be this. If someone tries to use different syntax, we do not have to cover that. We don't have to process it. And we don't have to worry about, oh, if they don't use the correct syntax, what happens to the program? Does it like do something unexpected? We don't have to worry about that. That's not part of the specification. We only have to correctly process a place command that follows the format specified and the other commands that also follow the format specified. So we'll have a place command, and again, excuse the mouse writing, with an X, a Y, and a direction, which I'll again simplify to D. If we represent the state of our robot using X, Y, and D, then obviously we can just map these directly in so that whenever the place command is provided and it has these 3 variables, well, parameters, I guess, then we can just immediately map the place command to the current state of the robot, and then we can use that as a starting point. Another thing which you need to worry about is how do we check if the robot has been placed? And since we're using these variables, one way to do that is to initialize one of these values, one of these state values, as a value that can never be achieved through normal usage. It can only be achieved before placing. So I've chosen to have the direction be that. And the way I've handled the direction is what allows me to do that. So let's go through that. So we only have to worry about 4 directions. The robot can only move in 4 directions: north, south, east, and west. And these are all linked to each other. It always goes north to east or north to west. It never goes straight from north to south, for example. It only ever takes one step at a time. And it's a cycle. Like if you go from north to east, 1, east to south, 2, south to west, 3. If you turn a 4th time in the same direction, you end up exactly where you started. So something interesting we can do is to remap this into a one-dimensional value. We go from 0 to virtually infinity, not literally infinity, because we have to store it as a data type, and the data type will have a maximum value. But for example, we have an integer, it can go up to, what, 60, 65,000, something like that. I don't remember the exact number. But we can map this to this by taking this arbitrary int value and doing a modulo 4 operation on it. And for those not familiar with modulo, it's basically just divide and then take the remainder after the division. So if we do 20 modulo 4, that's divide by 4, which equals 5 with no remainder. So the remainder equals 0, and this 0 is the thing we care about. So if we modulo 18 by 4, the remainder is 2, because it'll be 16 with remainder 2. And that lets us do a mapping where we convert north, east, south, and west into numbers. We quantify them. So, for example, we can make north equal... well, actually, I'll start off with what I've actually used in my code. And let me just pull it up real quickly on my end, because it'll be much easier to explain if I follow my own logic in the code. Okay, so in my example, north is 1, east is 2, south is 3, and west is 4, which equals 0, because 4 modulo 4, 4 divided by 4 is 1, with no remainder. So the modulo of 4 modulo 4 is 0. So that's 4 and 0 are the same for our purposes. So what that lets us do is every time we want to turn left or want to turn right, instead of worrying about sort of this cyclical two-dimensional thing, we only have to worry about this linear one-dimensional thing. How does that work? If we're facing north, so if we're facing north, we'll be, our direction will have a value of 1. And we want to turn right, the command is given to turn right. We can just add 1 to our direction, and we're suddenly facing east. However, if we want to turn left, because this is a cyclical thing, what we can do is actually, instead of turning left, which is difficult to translate into a linear one-dimensional space, we can turn right 3 times. So instead of adding 1, we'll add 3. So we'll go +1 to go east, +1 to go south, +1 more. We're now facing west. So instead of doing this, we've done this. And that just lets us convert this into this one-dimensional linear thing, where every time we want to turn right, we just +1. Every time we want to turn left, we just +3. And then when we want to figure out, oh, what direction are we facing, we modulo 4, whatever this value is, and then we take that and we'll know if the value is 1, 2, 3, or 0, then we're facing, respectively, north, east, south, or west. So that handles our turning. Movement is also pretty straightforward once we agree that we're using this set of variables to represent the state of the robot. So whenever we move, because our map can be represented like this, whenever we move, maybe I'll just draw it like this. Whenever we move east, we just add 1 to our x. Whenever we move north, we just add 1 to our y. Whenever we move west, we subtract 1 from our x. So it's the opposite of what we do when we moved east. Whenever we move south, we subtract 1 from our y. So north means we plus 1 to y. South means south means we minus 1 to y. And then east is plus 1 to x. And west is the opposite of east, where we minus 1 to x. Well, this should technically from, but you get the idea. So now we have a quantified way of turning, which is represented here as we discussed. We have a quantified way of moving, and we have a quantified way of representing the state of our robot. And by extension, if we know the dimensions of what the dimensions of the map are supposed to be, which we do when the program starts up, we can tell it how big the map is. We can use that information to act as though the map existed, even though it's sort of just a construct that we haven't explicitly defined. So that's all of the boring stuff. That's all reasonably straightforward. I'm sure there are several people who did something very similar to this when they were trying to take on Max's challenge. The esoteric part of my code is how I have handled place. Because I identified that place was where I could gain a lot of mileage in code reduction. Because when we are placing our robot, x will be immediately fed in as the value. So if we think about this in code terms, if we call our x, y, and d state, and we can refer to each of these, like we think of this as a tuple. So we can refer to state.x is this, state.y is this, and state.direction, or maybe just d for short, is this. So we want to make it so state.x equals this parameter from the place command. I'll just shorthand it. State.y equals this parameter from the place command. And state.d is this parameter from the place command. However, when we input the place, we have to input a string. We have one of these 4 options, north, east, south, or west. We can't input it as one of these numbers. If we could, that would be really great. It would save us so much trouble. But we can't. We have to input it using the prescribed specifications. So what we need is some function that allows us to remap from these numbers into these strings, or more specifically, remap from these strings into these numbers. We need some way to do that, some function to do that, and we want it to take as few lines as possible. The least number of lines possible would be none, but we just explained we can't use none. So we need something, we need at least one line of code that can transform a predefined set of 4 different strings and nothing else. We don't have to accept any other input valid and like actually correctly process it. Just these 4 to make these 4 consistently every single time. And the way I did that is through hashing, which we luckily covered in, what was it, 6.1. So the result of a hash will look like a random set of numbers, sometimes numbers and letters. It depends on what hashing algorithm and stuff you use. But for example, if I have a hashing function called hash and I input the word hat, the string hat. The result of that might be that. That might be the hash of the string hat. There exists some hash result such that if we input as a parameter of a hash function, if we input the input direction, and by that I mean north, east, south, or west. There is some hash where if we put this string as a parameter or as an input for the hashing function, we'll end up with a hash where, so we'll call this hash result the first, in this case it's actually just the first digit. So we will end up with a hash result where the first digit is always 1 if the input was north. It will always be 2 if the input was east. It will always be 3 if the input was south. And it will always be 0 or 4 if the input was west. And we can do that because these are the same. And we can extend that a little bit further. But I guess I'll get to that a bit later. That's not really part of the core explanation of what I've done. So we want to find a way to use a hash function to convert this to this. And in order to do that, we need to find some value, we'll call it t, or some additional input t, such that we can have, so our 4 inputs are north, south, east, and west, right? And we want to find some value t, where if we put it next to the direction that we're inputting, that will get that mapping that we're looking for. So if you only hash with just north, you're probably, I haven't checked, but you're probably not going to get, the first digit of the hash is probably not going to be 1. If you just hash south and nothing else, the first digit of the hash result is probably not going to be 3. What we need is for north and this value t to equal 1, and the first digit of the hash result. For south and some input t to equal 3 on the first digit of the hash result. And for east and some value t to equal 2 on the first digit of the hash result. And west and some value t to equal 4 or 0 on the first digit of the hash result. And well, we can extend this slightly in a way that's not too complex by saying that the north can also be 5 or 5 or 6 or 7. And instead of saying equals, we should say or 8. And this one can actually be or 9. Because if we modulo for 9, we end up with 1. So that's just a small optimization. So instead of finding a hash result for a single value for north, now we have 3 options. It's 3 times as likely to succeed. If we assume an average hash result distribution and some funky technical stuff, but let's just say for simplicity, we've made it 3 times as likely to find the result we need for north. We've doubled the chance it'll find the result for east, for south, and including the 4 to 0 mapping, which we started with, we've tripled the likelihood of getting the result we want for west. But the thing is, we need to find all of these results simultaneously for one value of t. So let's get into some code now. And this is the file which I submitted as my 1.1 submission. So we have the state that I talked about earlier. We have the input, which is just a string, and that's just reading the console and making it to lowercase. We technically don't need to handle the to lowercase, but it doesn't cost us anything to do it, so we might as well. You can see here we have handling for the map size, because if we look back at the specified map size, it must be not smaller than 2 by 2 and not larger than 100 by 100. So we can actually check that in the while loop that we have here. Is the and sorry, before we do that, we start the program with an argument for the map size, and because the map is square, oh, I haven't put that up on screen. Okay, because the map is square, we only need one value, and that lets us have that value for both the map width and the map height. So we take that single value from the arguments, which is arguments could essentially be renamed map size. Is the map size at least 2? Is the map size no greater than 100? And we do that every time, and we can do that as part of the while loop, so that we save having to put that on like a separate line. Every time the loop iterates, we read the console input, and then you can see we have one line to handle place, one line handles left and right, and then 2 lines handle move. But if you break this down, which we'll do a bit later, it would normally be in several lines. But before we do that, this is the code I use to find the magic number, is the value of t. So we spin up MD5 hashing, we iterate through, is this like 1 million? Yeah, 1 million iterations of the value I. We basically convert, this is a lot of just supporting logic, but the gist of it is we find a value for I such that we get what I was describing earlier, where we get this combination gets us a mapping of this for the first digit. That's all that's doing. It looks a lot more complicated because I have to do a lot of conversion on it. For example, to compute the hash, the input has to be bytes, so we have to convert it to bytes. And we also have to convert it to a string in order to access that first digit, because the logic that we've used is the first digit of the hash result. So like I said, a lot of it's just supporting code to make it do what we want. And I haven't done some of that optimization I talked about here. I'm actually just looking for 1, 2, 3, and 4. It's not even looking for 4 or 0. So it's quite sloppy. But it results in this. And if we break it down, and we can see all of the stuff that I've already talked about. So we store the state as a tuple called state, and we initialize it with values of -1. So I mentioned earlier that we can check for an invalid value to know if the robot has been placed. And one way to do that is I always check if the value of the direction is -1, because as I discussed, we only ever increment the direction positively on this one-dimensional linear number line thing. So that's what we can check for there. We have the string input, we have the conditions that I talked about earlier. This is the place command, we'll come back to that because it's the most complicated. So the left is straightforward, is the input, and the input is just the console read line. So is the user input left? And this is another way to say, has the robot been placed? This is just checking the direction of the robot. is the command to turn left, and is the robot placed? If it is, we turn left using the +3 that I discussed earlier. And the same thing for right, we +1 to the direction, which is just up here. It's not named, but that's what it is. The third item in the tuple is the direction. Move commands are all very similar to each other, where we check if the user input is move, and then we check these conditions. So has the robot been placed? As I mentioned, we always do that inline, because when you do it inline, you can make it one long thing. So you don't have to write the check on a separate line, you just do it all together, because that saves you some lines of code. Has the robot been placed? If we are simultaneously facing west and also not at the western edge of the map. So this is what I was talking about earlier, where we need to check if we're at the edge of the map. So we'll go back to drawing land, and we'll say we have let's do a 3x3 map to keep it simple. If the robot is at the west edge, we can't let it move west. South edge, we cannot let it move south. East edge, can't let it move east, so on. You get the idea. So whenever we are facing west and we're not at the western edge of the map, we decrement by 1 on the X. The opposite of west is east, so we actually increment 1 when we're facing east and also not at the edge of the eastern edge of the map. For north, we increment on Y when we're facing north and also not at the northern edge of the map. And then for south, if we're facing south and we're not at the southern edge of the map, we decrement the Y by 1. And this is just like debugging output, which is not required. It just makes your life easier while you're working on it. You can see that this is where one of the sections where we don't have a map object, where we sort of emulate having a map. And this could have been done differently, but I did it this way. Where every time we're at the west or south edges of the map, we check for the minimum map size. If we're also facing in that direction. And then for north and east, we check for the max map size. Once again, remembering that args is a single argument that we provided, which is essentially just map size. So we check, are we at well, in this case, it's map size -1, but it could just as easily be, instead of less than or equal to, it could be less than map size. And that way we can get rid of this and get rid of this, and it would be a little bit simpler, but I guess I'm a moron. So if you put that all together, you get this, and we've cheated a little bit because although place is all sort of one thing that's just really long, and I'll get to that in a second, our left, right is like actually one statement here followed by an else if and another statement, which is kind of janky. It kind of feels like cheating to do that, because if you let yourself put multiple if checks on one line, what's stopping you from putting 3 if you're allowed to do 2? What's stopping you from putting 4 if you're allowed to do 3? Like in my case, I followed what used to be a formatting rule in, I think, an old version of Visual Studio. It would let you put an if, else if, but if you tried to do more than that, it would break you down to the next line. The current version with default formatting doesn't seem to do that. It seems to let you do something insane like this. So if we run auto format on that, it doesn't actually move it down. But yeah, it seems a bit janky. So I follow that sort of arbitrary requirement of maximum if, else if. And that's what got me down to 9 lines. You could also do that. That's legal code. It will work. But it's a bit janky because you normally don't do multi-assignments like this unless the variables are related. So 9 lines. If we go back down to the place, we've sort of already talked about how it works. So we have a check for, are we placing the robot on a valid coordinate? So is it at least 1? Is the x coordinate and the y coordinate, are they at least 1, and are they a maximum of the map size? So are they on the map is essentially all that's asking. We have these 4 possible inputs for the, that's the 4th parameter because it's 0 index. The first parameter is of the input is place, it's the command. So we assigned a state, the x, the y, and then the direction, and the direction is sort of what we talked about before, where our magic number is 738, where we put this 3rd parameter, so that's this here, you can see it highlighted here. We put that with 738, and we end up with this mapping that I was talking about earlier, where we found the value of, well, we found a value for t, which is 738. And what I might do is hop over here, which is a copy of some of the code, and find out where the hell the main function is, which is up here. And so this is some old code, so let's get rid of that. Let's try to find the code that I used. I think it's this code here. And then we'll comment out the main part there. So if we run this, now I'll have to pull that up on. Okay, well that's going to be a bit difficult to show you in real time. What I might just do is switch to this temporarily, and we'll run that again. You can see it spits out a whole bunch of hashes, and one of the first numbers it spits out is 738, so that's the value that I used. But yeah, there's lots of values for t in this case. But that's what I ended up with in my submission. Now there's a lot of room for improvement, but I'll save the improvements for the follow-up video because this is already really long, and anyone who wants to delve into more pandas can do so voluntarily. So I hope you found that interesting.